Hey again, Dave here. I really hope you enjoyed Unit 1 because now it's time to start Unit 2. The first exercise is on relative humidity and orographic uplift. And again, let me introduce my technical assistant, none other than Mr. Jackson Howe, my son. Now the best part about this, stay here Jackson. The best part about this so far is Jackson has told me that he likes spending quality time with his dad. Is that correct, Jackson?
No.
Oh. That was very, very hurtful. Get out of here, kid. All right. So let's get started on this. Let me get the globe out of the way so you can see the board. Okay, first of all, absolute humidity. That measures the amount of water vapor in the air. Water vapor is, moisture in the air. It's humidity. So absolute humidity is measured mass over volume. The mass is grams of water vapor. The volume is a cubic meter. But the one we're going to work with today, and the one you see on the news at night, right, on the weather broadcast, is relative humidity. Relative humidity is a ratio. It's a ratio of what is actually in the air, that is absolute humidity, over the max amount of water vapor the air can hold. The max amount of water vapor the air can hold, the denominator in that equation, is determined by temperature. So the warmer the air, the more water vapor that it can actually hold. So I have two examples on the board, and you will have two problems to do in your short little exercise. So let me explain how to work these. So example number one, if I tell you the air temperature is 40 degrees Celsius, and that the max amount of water vapor the air can hold at that temperature is 50 grams per cubic meter, and the absolute humidity, that is what is actually in the air, is 30 grams per cubic meter, you'd set the equation up using this formula. So the actual amount of water vapor in the air, absolute humidity is 30 grams, the numerator. The max the air can hold at that temperature is 50 grams per cubic meter. So 30 over 50 is 60%. If you didn't know how to do that, you divide 50 into 30, move the decimal over 2 to get a percentage. The second example, the air temperature is going to be 22 degrees Celsius. The max amount of water vapor the air can hold at that temperature is about 20 grams per cubic meter, and the air is currently holding 15 grams per cubic meter. So AH is the numerator. The max amount of water vapor the air can hold at that temperature, denominator, 15 over 20 is 75%. So the two you have in the exercise are just like that. You should not have any problem with that, I hope. Then you have one question on something called orographic uplift. Orographic uplift occurs when air is forced into a mountain range. So in California, most of our storms, they come off of the Pacific. They're in the westerly wind belt. So that air, full of moisture off the ocean, is often pushed up against the coast ranges or up against the Sierra Nevada, and that air is forced to rise. That is called orographic uplift. So there's some problems for you to do. Actually, there's only one problem you have to do, and I'll give one example on the board here. So we're going to start an air parcel at 68 degrees Fahrenheit. And in this example, I want to know what the temperature would be of that same air parcel when it rises up to 5,000 feet, where condensation begins. Condensation is a gas to a liquid. That's when clouds start to form and we can get rain or snow. I'd like to know what the temperature of that air parcel would be at 9,000 feet, and then over on the leeward side, what it would be at 3,000 feet. Okay, when air rises or descends, it will change temperature. As air goes up, it cools off. As air comes down, as it subsides, it heats up. So as the air is rising and it's unsaturated, that means it's not forming a cloud, the air cools off at 5.5 degrees Fahrenheit per every 1,000 feet. On the other hand, if a parcel of air descends, it heats up at that same rate, the dry adiabatic lapse rate. If the air is rising and it's condensing, in other words, we're forming clouds, then you switch to the wet adiabatic lapse rate. So we'll only use that rate when the air is rising and condensation is taking place. So in this example, the air starts out at 68 degrees Fahrenheit at sea level. It hits the mountains and it's forced to rise. That's orographic uplift. Initially, it cools off at the dry adiabatic lapse rate. So what I did, I went 5.5 times 5. That's 5,000 feet. Okay, so it's cooling off at 5.5 degrees Fahrenheit per every 1,000 feet. So 5.5 times 5 is 27.5. I subtracted that from 68 degrees. 68 minus 27.5 gives us an air temperature at 5,000 feet of 40.5 degrees Fahrenheit. Now, from 5,000 feet to 9,000 feet, the air is rising and it's condensing. We're forming clouds. We're getting rain, maybe snow if it's cold enough. So I switched to the other rate, which is 3.2 per every 1,000 feet. That's called the wet adiabatic lapse rate. So I went 3.2 times 4 for 4,000 feet. It should go from 5,000 to 9,000, that's 4,000 feet. 3.2 times 4 is 13.2. Next, I subtracted 13.2 from the air temperature at 5,000 feet. So that's 40.5 minus 13.2 gave me a 27.3 degrees Fahrenheit at the top of the mountain. Probably snowing up there. Okay, as the air comes down the leeward side, I'm going to switch back to the dry adiabatic lapse rate, and the air is going to be heating. That means it's warming up as it comes downhill. The air compresses and heats at 5.5 degrees Fahrenheit for every 1,000 feet. So, from 9,000 to 3,000 is 6,000 feet. I went 5.5 times 6 is 33 degrees. Since the air is descending now, and it's going to be heating up, I added 27.3 to 33, and I got 60.3 over here on the leeward side of the mountain. So you have one problem to do on the exercise, and you do it exactly the way that I just did it. You use the different numbers, though, that I gave you. So at that point, I think that I am about done, and hopefully this goes easy for you. Take a photo of it, turn it into a Word doc like normal. Jackson, cut me off right now, please, sir.
Bye.
See you guys.